Yeah, so
Yes.
if you plot the error versus delta x, okay, for some schemes it is very smooth and monotonically decreasing, at least for the points that we have considered, okay, but others show this behavior, something like this, okay. So something is happening at this point, after which error starts increasing with reduction in mesh size, and that cannot be correct, because truncation error says that if your delta x reduces, the truncation error reduces, right? So there are two sources of error. Only one we have discussed in the class. So the sources of errors are total error. Let's say is truncation error. What is the source of truncation error?
So when we chop off definite like definite digits of a number, like uh, we introduce truncation error.
No, so truncation error is coming because we chop off um, higher order terms in Taylor series, right? That is truncation error. The second one, which we have discussed in the class, the second one is round-off error, which come because computer chop off um, many digits while storing data. Okay, so for example, the value of 1 over 3 is 0.333 bar, which means this is going indefinitely, okay, but computer store only finite number of digits in the memory. If you are using single precision calculation, it will be 8 digit, and if you use double precision, it will be 16 digits, right? So there is an error introduced in storing the number in computer memory, and that gives rise to the round off error. Okay, so let's say you want to compute du by dx at I using this backward difference approximation, plus this is order of delta x, this is truncation error. Okay, this we can derive from Taylor series. Okay, but this is order of delta x if you are able to store both the value of ui and ui minus 1 to indefinite precision. Okay, that is not happening. So what happens is that ui is ui plus some modulus epsilon, plus or minus, let's say plus, the sign doesn't matter. So this is the actual value, and this is what is stored in computer, right? So instead of 0.333 to indefinite value, it will store only 8 digits of the actual number, right? So this epsilon is what do we call it? If I am right, this is called as machine precision. For different computer, it will be different value. Okay? It is the smallest number your computer can store in memory. So machine precision is the smallest number that a computer can store. Okay, so while we are storing any floating point number, there is an error introduced inherently by the computer because of its ability to store only finite uh, number of digits, right? So if you substitute it back here, so what you are going to get is du by dx of I. I becomes so let's say this is u bar, which is what is stored in the memory. So u bar of I minus u bar of I minus 1 by delta x plus some constant times epsilon by delta x plus order of delta x, right? So this is again truncation error. This is round-off error, right? So as you see, the round-off error has 1 over delta x term. For very small value of delta x, this will dominate. For let's say delta x very small, this will dominate over truncation error. So the value of a round-off error will be more than the truncation error. So if you plot, let's say delta x versus the error, so the truncation error goes like this. So this is truncation error. Okay, and round-off error shoots up for very small value of delta x, and then it starts reducing for a larger value. So this is round-off error. Okay, and the actual curves look something like this. The total error looks something like this. Right. So this is why if you reduce the mesh spacing beyond a certain value, round-off error dominates and the total value of error increases. Okay, so why this is much more pronounced for, why is this effect more pronounced for second derivative? For example, if first derivative goes after a very sorry, somewhere here, sorry, that's a very bad. So let's say this is the first derivative. The second derivative will go much earlier. This is t square u by dx square. Can you guess why is it happening? Why is this behavior happening for second derivative?
So because we're using more terms.
That is that may be right, but actually here this becomes delta x 1 over delta x square instead of delta x. You get the point?
Yes,
So
sir.
if, yeah, is it clear for everyone? Tanmay, Anurag, Radhika.
So is it because our mesh is getting finer, so that's the reason this error is reducing?
What I'm so the truncation error has like order of delta x. So okay, let me write it. So when we say order of delta x, what we are having is some uh, constant times delta x. Right. This is what we mean by first order approximation, right? Delta x to the power 1. Right. So truncation error reduces linearly with mesh spacing for this particular scheme because this is a first order scheme, right? But if you look at the round-off error, it has 1 over delta x term. For very small magnitudes of delta x, round-off error dominates truncation error. So that you can see the curve here. The blue one represents round-off error, which is very large for small mesh spacing, and its magnitude reduces if delta x increases. And truncation error has the opposite behavior. Is that clear?
Yes, sir.
Any other questions? No? So those of you who could not finish this part, could you spend some time in the evening and finish implementing the fourth order second derivative stuff. And Nitin, please post the answers by today.
Sir, do we have to submit the code and the graph?
No. This is for your own practice. Assignments I'll start giving soon.
Okay, sir.
So this is for you to get started with implementing some small things. Yeah. So Anurag,
Yes,
you
sir.
make sure that you will finish it by today.
Sir, I got the graph, but it is
Okay.
not exactly the same way as unmolding.
Okay, so I will ask Nitin to post the answers. You can compare. Uh, at least initially, you should get the fourth order behavior.
Yes, sir.
Okay. Very good. Then I'll stop here. Then. And if you have any questions, you can always send me a message. Okay. Yeah. See you.
Yes, sir.